Hi guys, welcome. This week we are looking at week 7. 3 lessons we're covering are 97, 98, and 99. So those will be our 3 for this week. So nearing the end of the unit. So let's look over at lesson 97 on page 646. All right, so we're looking at recursive rules for sequences. So again, sequences, like a function, even though we can't put 0 in, we always start with 1 for the first term. It's similar to a function or a rule that we have. So n is the term, so that always goes 1, 2, 3, 4, 5, obviously, and continues on sequentially. And then a is our value, so 3, 6, 9, 12. So the following formula will generate any term of the sequence above. The notation a of n refers to the term value a at position n. So the subscripts only indicate position. They're not involved in the calculations. So a of n, if we put in 3 for n here, that means we're putting in 3 for n here. It's not a times 3 or anything like that. It's just indicating the position that we're looking at. And then we can put it in and calculate it. Or if we say a of 7. A of 7 means we put in 7 anywhere there's an n in our rule, and 3 times 7 is 21. We can also write formulas that show how a term in sequence relates to the preceding term or terms. In the previous sequence, the value of 3 of the term is 3 more than the preceding term. We may write the rule this way, even though it's going to be a little bit more complex. And we have a of n equals a of n minus 1 plus 3. So if we're saying a of 2, we put in 2 minus 1, so a of 1, whatever that was, plus 3. So it's another way to write it. When we have this a of n minus 1, that means our previous term plus or times or to whatever power. Then we can find the next term by adding 3, or in some examples, multiplying or subtracting or whatever it is. It's going to apply to the rule. This kind of formula or sequence is called a recursive formula. When we write recursive formula, we also indicate the first term. Again, if we don't know where we start, then there's no way to come up with the rule. So a of 1 equals 3. So if we're looking at this, write a recursive formula for the following: 2, 4, 8, 16, 32. Well, let's first see what's going on. Well, 2 plus 2 is 4, but 4 plus 2 is not 8. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay, so now, since it's worked out for more than just 2 of the terms, or 2 of the values, we think we have what we're looking at. So 2 times 2 times 2 times 2 times 2 times 2. Now having a rule is going to make it a little bit easier than just take it out to the 20th term or the 50th term. If we can write the rule, then we can use that to plug in a number for n. So 2 times whatever the previous one is. So 8 times 2 is 16. 16 times 2. So this term, we look back at the previous one, and then we multiply it by 2. So this would be the rule that we come up with, because a of n minus 1 tells us our previous. That's just saying whatever number's in here, our 5th term. 5 minus 1, we're looking at the 4th term, and then multiplying it by 2. So again, the 5th term would be right here, so we'd look back at the 4th term and multiply it by 2. 2 times 16 is 32. So a of 1, first term is 2. A of n equals 2 of a n minus 1. 2a n minus 1. Example 2, this formula shows how to find any term of a sequence. Use the formula to find the first 4 terms of the sequence. 1 plus 2n. Okay, so a of 1. Put in 1 for n. 2 times 1 is 2, plus 1 is 3. 2 in for n. 2 times 2 is 4, plus 1 is 5. 10 for n. 2 times 10 is 20, plus 1 is 21. Okay, so how could we write a recursive? Well, it's going to go 3, 5, 7, 9. all of our odd numbers. It's going to keep going. Well, we could say our first term is 3. And then our previous term, or a of n minus 1 plus 2. Because 3 plus 2 gives us our next term. 5 plus 2 gives us our next term. 7 plus 2, and continuing on. If we're given the recursive formula, a of 1 equals 5, so that's our starting point. A of n equals 3 times a of n minus 1, or our previous value. Find the second and third terms. Okay, well, the first term is 1. So the second term, if we put 2 in for n, 2 minus 1 is taking us back to our first term. So 3 times 5 is 15. Okay, third term, well, this a of 3 is going to be, okay, 3 minus 1 is 2. So our second term we just said was 15. So 3 times 15 is 45. And we'll get the hang of these sequences. We don't use a ton, but they're really, really important, especially as you apply them to all different aspects that we get into. So we'll do the practice set when we get back together, do some more practice with them. So that is one of our lessons. Now, lesson 98, we're looking at relations and functions. Okay, make sure I'm still presenting. So a relation is a pairing of two sets of information. In a phone book, names are paired with phone numbers. The name-number pairing is a relation. A player's jersey paired with the number of points they scored, or number of fouls they committed, or whatever. So we have a pairing. Right? Number of tickets, total price. If we buy 0 tickets, cost 0. If we buy 1, it's 7. 2, 14. 3, 21, and so on. Not all relations are functions. That's important to know. So we can still graph different points. Just because we have points on a graph doesn't mean it's a function. So the easiest way to test for a function is to use the vertical line test. So if I pass a vertical line, start it and just sweep it through right to left or left to right, and it crosses more than one point at a time, then it's not a function. So if we go over here and we look at we've worked a lot with linear functions. Well, if we take a vertical line, okay, it's only going to cross one point everywhere on the function. If we look at a parabola, we haven't done a ton working with these, but it looks kind of like a U-shaped right there. Draw a vertical line. Yeah, it's only going to cross one point of our function. Even though it's going up sharply, it's not going directly up and down. It's still moving outward, left and right. But if we have something like this shape, okay, we have this shape of a graph, is it a function? Well, does it pass the vertical line test? No, because it crosses more than one point. So the vertical line test is the easiest way if we're given a graph to see if it has a function. So in this example that they went through, each input value is not paired with exactly one range value. So we have an x value, or our input right here, our domain values, and we have two outputs. So we think about our formulas, y equals 5x or y equals x squared. We put in an x value and we get one y value. We put in an x value and get two different y values, then it's not going to be a function. So all that to say, again, the easiest way is it would not pass the vertical line test. So looking at this, we don't even again, you could just take your ruler across your book and kind of sweep it from left to right to see if it crosses more than one point. A would be good. Yes, that's a function. B Even though this is going down steep, it's still not going to cross more than 1 point, whereas C, this S-shaped graph, obviously we could use the y-axis as our vertical line, and it hits 1, 2, 3 points. So if we put in X for 0, we should only get one output, but we actually get 1, 2, 3 outputs. So C is not a function. If we sketch a circle, we've done shapes in the coordinate plane, parallelograms, triangles, squares, circles. If we sketch this in the coordinate plane, center is the origin, radius of 1, 2, 3, 4, 5. The circle's graph is a relation, lists 4 pairs of points in the relation. Is the relation a function? So it can be a relation and a function, but a relation doesn't mean it has to be a function. This one, again, we can go look at our ordered pairs, or we can just use the vertical line test. Again, there's no horizontal line test. Again, it can, back to our example here. This one would not pass the horizontal line test, but there is no such thing as the horizontal line test. So this is still a function. So we really want to look for vertical. Again, if we use the y-axis, go straight down, it's going to hit a point here and a point here. So it is not a function. Okay? And if we looked at 0 and getting 2 different outputs, we should not have that if it is a function. For every input we have, we should have 1 output and not 2 outputs. Again, X is our independent or our input, Y is our output. Similarly, we can use scatter plots to present the data in relation. In fact, recall that sometimes plotting data in a scatter plot helps quickly reveal the correlation or relationship between the sets of data. To determine whether there's a correlation among data, we draw the best fit line of best fit. That can help us identify a trend in the data stemming from a relation. Okay, so if we're looking, I guess let's read through it. Near the beginning of the lesson, we saw that Preston gathered data on the number of students at school and the time he arrived. Look again at the graph where we plotted the data because the entire set of data can be conveyed as a distinct point on the graph. This is the same as a scatter plot. Okay, so we have different points throughout our graph. So we just plot them, usually focusing in on the first quadrant, depending on what real world example we're looking at. A lot of times we won't have negative numbers, so we're just looking at the first quadrant. Sketch the graph of the function that models the data, draw a best fit line on the scatter plot. Now you can use the line of best fit, sometimes called the trend line, to make predictions about the data set. So the minutes before school, the number of students. So minutes before school, 1 minute before, 2, 3, 4, 5, all the way out to 12, and the number of students. Now, according to your graph, how many students might Preston see 10 minutes before school starts? 10 minutes before school. Line of best fit is going to fall, again, best represent this. Obviously, looking at these points, it would be linear, and it looks like our slope would be negative because it's going down from left to right. So at 10, we could predict that there would be about 21, 22, maybe 23 students right there, depending on the line of best fit. At 8 minutes, again, go over 8 up to our line of best fit, about 32 or 33 students that we would have. And we'll talk more about line of best fit. Sometimes we have a 1 is perfect correlation, -1 is perfect, negative correlation, and then we have a 0 where there's no correlation. So I've seen even, professionals that'll take, something like this. If it looks like a circle, there not really is a line of best fit. There's not really a line of best fit there, but they'll try and take this and kind of make it look like there's a line of best fit, which there's really not. So again, 1 would be perfect correlation, all the points fall on the line. We know in the real world it doesn't usually work out like that, okay? Or -1, perfect correlation, but the line is going down, or anywhere in between where, like I said, it looks like a circle and there is no line of best fit. So we'll talk about that more and more. We talk a little bit more about statistics. So we'll go over that, practice that problem in class. And then the last one we're looking at for week 7 is lesson 99, inverse variation. So we've talked about direct variation. Direct variation, something's directly proportional. If it goes through the origin and is linear, then it's direct variation, y equals k times x. Now we're going to have inverse variation, where we still have a constant, but we're dividing it by x. So as x gets bigger, y is getting smaller. As x gets smaller, y is getting bigger. So that's why it's inverse. As one gets bigger, the other gets smaller, and vice versa. So it's inverse variation. We're still going to be able to identify our constant. Again, if we rewrote this, okay, we can write it in terms of k, just like we did with direct variation. We can write it like that as well, which is going to be helpful sometimes if we're given, different examples where 3 workers complete this much work. How many will 4 hours of workers complete, assuming they work at the same pace? So we'll be able to use this formula for some different things. And then the graph of inverse variation, as we'll see here in a second, is not going to be linear. So we talked about direct variation. Okay, we can write it in terms of k, just like we did for inverse variation. Inverse variation, as we showed, can be written as k, or in terms of y, we would divide both sides by x to get y equals kx. So that's inverse variation. So we'll look down at a few examples, but so the more people that show up to family dinner, the less they're going to see. If we're making a set amount of cornbread or whatever, and more people show up and they all eat the same amount, then you're going to get less and less and less. So the more people that show up, the less you're going to get to eat. Okay, so it's inverse proportion. As one number is getting bigger, the other is getting smaller. So that's inverse variation. So Trin travels 120 miles to visit his friend. If he averaged 60 miles per hour, then he takes then the trip takes 2 hours. So 60 miles per hour, 2 hours. If he goes 40 miles per hour, okay, what's going to happen? And we can multiply both sides by x to get that. So let's look back at our problem. So 60 miles an hour takes 2 hours. So k, x times y, 60 times 2 is 120. So our constant is 120. And we need to know that. So if we put in 40 for x, okay, well, our k is 120. So y, where 40 equals x, is going to equal 3. And what was our next one? 30 over x equals 30. It's going to be 4. And 20. It's going to be 6. So we keep filling it. And we notice as x, our input is getting smaller, our output is getting larger. So the slower we go, or we go down in miles per hour, the longer the trip is going to take. Okay. The faster we go, okay, so miles per hour is going up, then the time is going down. So it's an inverse relationship. One's getting bigger, the other's getting smaller, and vice versa. Okay, so we fill in all of those. The quantity that remains constant, our K, is 120 miles an hour. And we showed that the rates are inverse. We found 40, 30, 20 miles per hour, the time that it would take. Looking at rate times time, it's going to give us this shape of a graph. So inverse variation is going to look like this. Not always exactly like this, but it's going to take this general shape. So if we continued on with this all the way down and plotted, so I don't want to say the tough part, but the thing we got to think about with this is we need more than 2 points. When it's direct variation, that means it's linear. We know a line, we need 2 points in order to graph a line. Well, this, we're going to need a lot more than 2, because if we just take these 2 versus these 2 versus, these 2, we're not going to get the general shape of the graph. So we need to have quite a few points in order to show what this looks like. And if we're looking at this, so let's just take a look at our own. So if we go into our y equals, and let's just say our constant is 5 divided by x. Let's take a look at that. We notice that it would also be over here because we can put in negative values for x, and we're going to get negative values for y. 5 divided by -1 is -5. Usually real world examples, we focus in on the first quadrant, as we said, but again, it has kind of this, descending shape. And you notice it gets closer and closer and closer to the x-axis. It gets closer and closer to the y-axis. Will it ever cross? Well, let's go into our table and take a look. So again, where x is 1, it's 5. Where x is 2, 2.5, 3, and 1 2/3. Where it's 4, it's 1.25. But when it's 0, we get an error. So if we put in 0 for our input, there's nowhere that it's going to touch on the graph, because we go back here, we cannot divide by 0. So that's why we get an error message. So inverse variation, there are going to be some values for x that we cannot put in because we can't divide by 0. So that's why it'll show up, gets closer to that axis as we approach it, but x cannot be equal to 0, so it's going to continue on infinitely up this way and get closer, 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 but it's never actually going to be where x equals 0. So just be aware of that, a little side note. So we may have some examples in the future where we have to say x cannot equal, in this example, it was just 0 because we were dividing by x. X cannot equal 0. Or if it's a linear equation, it goes on infinitely in all directions, and we can plug in any x value and get a y value. That's not the case with inverse variation. All right, and we will see these types of problems. So let's look at this one. It says, robots are programmed to assemble widgets on an assembly line. So again, the robots are programmed, they're going to work at a set rate. This may work for human workers, maybe not. Some people work faster than others, or may make each other goof off or whatever. You guys have worked in groups. So again, when we're doing these types of problems, we're assuming that it's constant. So we have robots are programmed to assemble the widgets on an assembly line. The number of robots working N and the amount of time it takes to assemble a fixed number of widgets are inversely proportional. If it takes 10 robots 8 hours to assemble a truckload of widgets, how long would it take 20 robots to assemble the same number of widgets? So let's first start out with what we have. So say, what is it? Robots working N, and that's going to be our input. Okay, that's our independent, because the amount of robots is going to affect the time T. So again, we could think of this as our x, because we usually do x and y, but this one we're doing n and t. So again, our xy equals our constant, or our n times our t equals our constant. Our first value we were given was 10 robots. Takes 8 hours. So 10 times 8 is 80. That's our constant. Okay. So now we can use that. Let's go back to, that's right, in terms of t equals k, our constant, divided by n. So as the number of robots go up, the time should go down. Okay, our constant, we know k was 80. Let's go ahead and put that in for our k. Okay, so we found our constant. That's important. We need to have that. And we want to know, what did it say? The number of robots goes up to 20. What's the time going to be? Well, let's put in 20 for n. 80 divided by 20, 8 divided by 2 is going to be 4. So t equals 4. So if we double the number of robots, then the time gets cut in half. So more robots, less time. Less robots, more time. More robots, less time. So that's our inverse relationship. As one went up, the other went down. And we'll see this with types of problems like people painting a house or whatever. If they work at the same amount, you go from 3 workers to 5 workers or whatever. So first thing, find your constant, your k. We need to know that. And then from there, you can plug it into your equation. We could even graph this, use x and y equals 80 over x. In our calculator graph, you'd probably have to adjust your windows, but it would show us what the shape of our graph looked like. Okay, I think, yeah. Okay, so we'll go over these practice set problems when we get to class, but that is it for this week. We're nearing the end. The week after this, we'll just have the one lesson and the review. We'll see you guys then.